Hello, this is the Test 3 Solutions, Work, Energy, Momentum, and Angular Motion. Number 1, determine if the work is positive, negative, or if there is zero work done in the following examples. Part A, a weightlifter lowers a heavy bar from above their head to the ground. So the bar is moving downwards, that is the displacement, and they are lowering the heavy bar from above their head, so the force they're applying is going to be upwards because they will be lowering the bar slowly. I don't say they just let go. I don't say they throw it down. So in this case, this is going to be negative work. B, a weightlifter holds a heavy bar in place above their head for 3 seconds. This is going to be zero work. That's because the bar does not move. The delta D equals 0. 2, a box is being pulled across a horizontal floor for a distance of 3 meters by a rope. The rope makes an angle of 60 degrees between itself and the horizontal and pulls on the box with an applied force of 120 newtons. How much work is being done on the box? So work is equal to FD cosine of theta. However, in this case, theta is the angle between the displacement and the force. Theta is not 60 degrees here. The force is 120 times the cosine of 60 degrees, because that is the x component, the parallel component of the force. That is parallel to the displacement. We're told the displacement is 3 meters. And then this is the cosine of 0 degrees, because the parallel component of the force is, well, parallel with the displacement, and they both point in the same direction. They are parallel, not anti-parallel. So this gives us 180 joules as our final answer. Number 3, explain why pulling on the box from question 2 with a more vertical force makes pulling it easier, even though less work will be done on the box. So if we pull with a more vertical angle here, we increase that 60, so it's above 60. That will lower the component that is parallel to the displacement. So that is why less work will be done. However, increasing the vertical component will lower the normal force required to balance gravity. Therefore, reducing the force of friction. And this, with a lower force of friction, means it is easier to move the box. So that was the first page of questions. Question 4. A block of mass 2 kilograms is released from rest at a 1.5 meter tall frictionless ramp. The block slides down the ramp and reaches a horizontal surface. The horizontal surface has a coefficient of kinetic friction of 0.25 and a length of 0.8 meters. At the end of the rough horizontal surface, the block runs into a spring with a spring constant of 800 newtons per meter and compresses it until it momentarily stops. Find the maximum compression of the spring, that is X. And a hint is here, think about what form or forms of energy are present in the very beginning and the very end. Basically, let's use this. What that means is in the very beginning, we only have gravitational potential energy. It's released from rest. It's not spinning. There's no spring that's compressed in the beginning. There's nothing. Just gravitational potential energy in the beginning. At the end, when it maximally compresses the spring, well, it's on that horizontal surface, so there's no gravitational potential. It's not spinning. When it momentarily stops at the maximum compression, there's no kinetic energy. So we only have elastic potential or spring potential energy. Now there is friction on that horizontal surface, so some of that gravitational potential energy will be turned into work. So in the end, all of my energy is either stored in the spring or it was lost due to friction in the form of work done by friction. So this is how we set up our equation. I'm going to substitute in and do some slight rearranging at the same time here. Now, work. This is going to be equal to the force of friction times the displacement times the cosine of phi, the angle between the force and displacement. Now I'm going to continue substituting in without rearranging for now. Now the force of friction, that is equal to mu times, now the force of friction is on the horizontal part, so I don't need to worry about breaking anything into components. The force of friction is equal to the normal force times the coefficient of friction. So I have my coefficient of friction times the force of gravity, because the normal force will be the same as the force of gravity on this horizontal surface. And I have the cosine of phi. Rearranging everything, I will get x equals the square root of 2 times mgh minus mu mg cos phi all over k. Yep, okay. And subbing in some numbers, I get 2 times 2 kilograms times 9.8, make this bracket big, times, I think the height was 1.5, yep. I think this was 0.25, yep. And I got 2 kilograms, 9.8, and the angle between them was 180 degrees. All of that on the top multiplied by 2 over, I believe, 800. And plugging this all in, we get about x equals 0.25 meters. So you did not need to use kinetic energy at all, because the total energy at the beginning has to equal the total energy at the end. Now you absolutely could have used gravitational potential equal to kinetic energy, and then used that to find the initial velocity before friction, and then you could have found the acceleration change due to friction, or the change in energy due to friction at that point, and then you could have found the initial velocity as it hits the spring, and then you could have done kinetic energy in the spring. So you could have broken this up into 2, 3, or 4, or 5 steps, depending on how far back towards kinematics you went, but it was perfectly doable with this here, without using kinetic energy or kinematics at all. 5. 3 masses are placed in a line. The first mass is 30 kilograms. So I will put this as mass A, and is 4 meters to the left of the second mass. So here I got 4 meters. I have a second mass B. It is 40 kilograms. And the third one is 35 kilograms and is located 2 meters to the right of the second mass. Call it mass C. Find the center of mass of the system. I am going to choose A as my reference point. No real reason other than I know that if I choose A, all my distances will be positive because everything is to the right of A. I just want to deal with everything being positive. Don't want to have to forget a negative or worry about forgetting a negative here. So, writing this out, for A, I get 30 kilograms times a distance of 0 meters, because A is my reference point, plus 40 kilograms for B, times a distance of 4 meters from my reference point, and plus for C, 35 kilograms times 6 meters. So from my reference point, C is the 4 meters plus the 2 meters away. So that's why I have 6 meters down there for the distance. And on the bottom, I just have the sum of all my masses. Plugging this all in, you should get about 3.5 meters. And what this means is that my center of mass is about, actually I will color code this into blue. My center of mass is about right here. So therefore, the center of mass is about 3.5 meters right of mass A. So that was questions 4 and 5. Question 6. This was the big one. A pulley of mass 0.9 kilograms and radius 0.05 meters has a string that passes over it and is connected to two masses on different ends of the string. Mass A is 1 kilogram and mass B is 2 kilograms. The system is released from rest with both masses at the same reference height of 0 meters. What is the angular velocity of the pulley when the masses are both 1.5 meters from their starting points? So what is actually going on here? I'm going to have a before and after here. And before, I got mass A, I got mass B. Let's say that this is where height is equal to 0 meters. That's the reference point. In the beginning, my total energy is equal to 0. Nothing's moving. Both masses are at the reference height. I mentioned that in the question that they are both at a reference height of 0 meters. So there is 0 energy in the beginning here. And so if I now have, I'm just going to continue my reference height. Still have A, still have B. So I know that A is moving upwards and B is moving downwards. And I know that this distance here is 1.5 meters. I know this distance here is negative 1.5 meters. And I know that the pulley is spinning. So I have 5 different forms of energy here. However, I know that all of them added together has to equal 0 joules. There's nothing adding energy to the system here. Nothing at all. Instead, the masses have just been released and allowed to freely fall. So, let's go ahead and write this out. I know that everything is equal to 0. So, I know that I have EGA plus EGB plus EKA plus that's supposed to be EK B plus EKR of the pulley. So I have the gravitational potential energies of A and B, and I have the rotational kinetic energy of the pulley, and A and B are both moving, so I have kinetic energy from both of them. So I have 5 different types of energy here, and added up, they all equal 0. So plugging in, or substituting, I guess, for now. So mg HA plus mghb plus 1/2 mv squared plus 1/2 mv squared plus 1/2 I omega squared. Now, something we should note, the velocity of A and the velocity of B and the tangential velocity of the pulley are all equal. So VA equals VB equals VT. These are all equal in magnitude, I should say. So these are all equal in magnitude. So that's why I don't have A's or B's on either of the velocities in this line down here at the bottom of the screen. So let's go ahead and plug in. So I have here that for mass A's mass is 1. So I get just 1 times 9.8 times the height, which is 1.5 above, plus for B, I get 2 times 9.8 times minus 1.5, because that is below our reference point. This is plus 1 over 2. This was for A, so this is a mass of 1 v squared plus 1/2 times the mass of B is 2 v squared plus 1/2. Now, you could go ahead and calculate this a couple of different ways. I'm just going to substitute in for V here. And for the I, this is a solid disk, the pulley. So this is 1/2 mr squared. And for omega, I get V squared over R squared. I'm just going to go ahead and cancel those out. And doing some simplifying here, I'm going to add together my gravitational potential energies to get negative 14.7 plus 1/2 v squared plus v squared plus 1/4 times the mass of the pulley, which is 0.9, v squared. I believe it was 0.9. Yes, 0.9 for the mass of the pulley. Okay. Doing a bit of simplifying and rearranging, I'm going to get that 14.7 equals the v squared times 1/2 plus 1 plus 0.9 over 4 is then equal to V is then equal to the square root of 14.7 over this whole fraction, which simplified only a little bit is 3 over 2 plus 0.9 over 4. And this gives us a velocity of 2.919201797 meters per second. Now, this is not my final answer. That's why I kept so many decimal points here. Going back, I'm going to sub this back into my formula for omega. No real reason why I subbed in V over R for omega. I could have solved it without doing that, but this is how I thought to solve it. So this is where I'm going to plug in that long decimal again. 797 all over 0.05, and that gives me an omega of 58.4 radians per second. And the direction here would be towards B. So in this case, it would be this way for me. Now, I'm not too picky about the direction because I don't tell you which side of the pulley that A and B are on. Just note that, of course, it's going to spin towards B because B is the heavier one. That's what's going to go down. Not too picky about the direction there because not everybody's going to tell me what side A is on, what side B is on, and I didn't ask. So that was question 6. It was definitely the most difficult one here on the test. So if you have questions, please ask. Number 7. An 80 kilogram puck slides to the right with a speed of 6 meters per second on a frictionless surface and collides head-on with a stationary puck of mass 1.5 kilograms. The collision is perfectly elastic and the contact lasts 8 milliseconds. After the collision, the heavier puck moves to the right at 4.17 meters per second. Find the final velocity of the 0.8 kilogram puck. So this was a conservation of momentum equation, or question. So I have my initial momentas for each one, and they equal my final momentums for each one. We're told that B is initially at rest, so that is 0. So I get mv for A equals mvf for A plus mvf for B. Plugging in numbers, I get 0.8 times 6 equals 0.8 VFA plus 1.5 times the 4.17 given. And solving for this, I get a VFA of negative 1.8. I won't skip that many steps. I get a VFA of 0.8 times 6 minus 1.5 is 4.17. 0.8. And the negative VFA of negative 1.81875 meters per second. So this is going to the left. I'm choosing right to be positive and left to be negative. So I know that is going to the left. So the first puck rebounds off the second one and starts moving backwards. Part B, find the impulse delivered to each puck. I will be using the fact that impulse is equal to the change in momentum. So for puck A and for puck B, I'll be doing these separately here. A, this is equal to the final momentum minus the initial momentum. So 0.8 times negative 1.81875 minus 0.8 times 6. This gives me negative 6.255. And we'll use the unit of Newton seconds because it is smaller and easier to write. For B, this one is a little bit simpler, 1.5 times 4.17 minus 0, because it had no initial momentum. So final minus initial, when in the initial 0, it's just whatever the final is. In this case, that is 6.255 Newton seconds. And because impulse is defined as the change in momentum for both of these, they should be the same with opposite signs or opposite directions. C, find the average force acting on each puck during the collision. I will be using the other equation for impulse, and this is where I got my units of Newton seconds from. Impulse is equal to force multiplied by time, so units of force multiplied by units of time, Newton seconds. We are looking for the force this time though, so rearranging, that is just going to be the impulse divided by time. Doing it for A and B separately, because we were asked for each puck in both of these questions here. So the force on A is negative 6.255 divided by, now this was milliseconds, so this is 8 times 10 to the negative 3 seconds. For B, this is basically the same, except it is positive. This gives me an answer of negative 781.875 newtons. And for B, again, the exact same answer, but positive. So that was question 7. Question 8. A solid disc of mass 5 kilograms and radius 0.4 meters is initially at rest and mounted on a frictionless axle. A constant torque of 6 Newton meters is applied to the disc for 4 seconds. Part A, find the angular acceleration of the disc. I'm going to use this torque formula because I'm given everything I need to find this. I'm given the torque, I'm given the mass and the radius of a solid disc, and I know that for a disc, the moment of inertia is equal to 1/2 mr squared. So alpha equals 1/2. Oh, the torque is on top. Is equal to torque divided by 1/2 mr squared. Plug in values here. I have a torque of 6 on top over 1/2 times 5 times 0.4 squared. I get an alpha of 15 radians per second squared. Part B, find the angular velocity after the 4 seconds. So I'm told that it starts at rest, so my initial omega is 0. My final omega is what I'm looking for. Alpha I just calculated was 15, and the time is 4 seconds. Just adding units to those numbers. So I'm going to choose one of my constant angular acceleration equations, and I'm going to choose this one here. My initial angular velocity is 0, so my final one is equal to alpha t, which is equal to 15 times 4. So my final angular velocity is 60 radians per second. C, find the angular momentum after the 4 seconds. So we got a couple of different formulas for angular momentum. I'm going to use the I omega formula because I already know I have the moment of inertia, and I just calculated what omega f is. So this here is going to give me 1/2 times 5, which is our mass, times 0.4 squared, which is our radius, times 60, which is going to give me 24. Now, the 5 had units of kilograms, the 0.4 was in meters, so that is meters squared, and the 60 had units of radians per second. So that there is my answer for C. For D, find the instantaneous power delivered by the torque at 4 seconds. Power is equal to just torque multiplied by the angular velocity. In this case, that is our 6 multiplied by the 60 that we calculated, because that is the angular velocity at 4 seconds. So my power is 360 watts, or joule seconds if you would prefer, or any other mix of equivalent units. There's a whole bunch of different ways you can write that. So that was question 8. And lastly, questions 9 and 10. A figure skater leaps into the air and spins with their arms out with angular velocity ω1. On their second jump, their arms are held tightly against their chest, and they have a new angular velocity of ω2. Everything else about the two jumps is identical. Determine which jump has the larger angular velocity and to explain how you know using inertia. So I am going to say that the jump where the arms are tucked in, so on the second jump, the angular velocity is larger. And I'm going to say this because when their arms are tucked in, the moment of inertia is smaller, so omega must be larger because everything else is the same. And for 10, two hockey players are skating towards each other and collide. Both of them fall down on the ice where the collision happened and come to a stop momentarily. What type of collision is this? They both come to a stop. This is inelastic. What quantities are conserved and what quantities are not conserved? Momentum is conserved. In inelastic collisions, momentum is conserved and kinetic energy is not conserved in inelastic collisions. So kinetic energy is not conserved in inelastic collisions, and momentum is conserved in inelastic collisions. That was everything for the test. If you're wondering why this says 10 pages instead of the 8 that you actually wrote, it's because I added an extra page, and then I had my formula sheet, and then I had the extra page. This is so that if I ever use this again in the future, it will be, or the students in the future will be able to actually rip off this last page with the formula sheet and not worry about that final page that they rip off having a question on it like we did today during the test. So if you have questions, again, please email me, ask me in class, and I will see you tomorrow.